Alright, this circuit problem is called a combination circuit, and we'd like to do a circuit analysis calculating the voltage, current, and power at each resistor. And notice that what's different about this circuit is we have two resistors which are in parallel with each other, which then are in turn in combination with a 2 ohm resistor in series combination with the 2 ohm resistor. So what we need to do is break the circuit down, find out the total current, and then we can work back to calculate all the different quantities that we want. So here's how we get started. We can find the total current by collapsing the circuit, and we begin with what we do is we begin with the 6 and the 12 ohm, which are in parallel. We know from our parallel relationship that 1 over the parallel branch would be 1 over our 6 ohm and 1 over our 12 ohm resistor. So if we keep working with that, we know that this is the same as 2/12 plus a 12th, or what we would get for our sum here is going to be 3/12. And inverting that, we would find out that the parallel resistance is going to be 12/3, or equivalent to 4 ohms. So we can replace our two parallel resistors with an equivalent 4 ohms worth of resistance right here, and that allows us to continue to simplify the circuit, okay, to find the total resistance. So now we can see that we've got an equivalent 4 ohm resistor in series with the 2 ohm resistor. Excuse me. And what we know there is that our series relationship should be the sum of these two resistances. So we just add our 4 ohm resistance in there, and what we see is that in this case those sum together to an equivalent 6 ohm, so we can redraw our circuit as if it's one 6 ohm resistor. So now we've completely collapsed our circuit down, and we realize that those three resistors are behaving as if one resistor would if it was a 6 ohm resistor. So then we can apply Ohm's law to this entire circuit, right? Total voltage should equal the total current times the total resistance. And what we would see using our 18 volts and our 6 ohms is that the total current is going to end up being 3 amps. So we know that the total current is going to be 3 amps coming out of our power supply. So the next step now is we can use that information and we expand the circuit back, all right, applying the known quantities and Ohm's law at each location. So we can take a look now, realizing that we've got 3 amps coming out of here, and this allows us to start calculating our quantities. We know we'd have 3 amps coming through the 2 ohm and a 3 amps coming through the equivalent 4 ohm. So we should be able to begin to calculate our voltage across each one of these. Across the 2 ohm resistor, the current through it would be, right, the 3 amps times its resistance. So we can take the 3 amps times 2 ohms, and we know we'd get 6 volts. So we know that we're dropping 6 volts of potential across our 2 ohm resistor. Now this 4 ohm branch really is two resistors, but the same potential is going to be dropped across each resistor from before. We could just apply Ohm's law to this equivalent 4 ohm resistor. We know that there's 3 amps going through it, right? It's 4 ohms, so this gives us 12 volts dropped across the 4 ohm resistor. Okay, now, or you could have taken 18 volts minus the 6 volts, and that would have also given you 12 volts. Remember, that's a statement of the conservation of energy as we would come through here. If we're going to start with 18 volts, drop 6 volts here, we know that we're left with 12 volts to be dropped across the 4 ohm resistor. Okay, so far we know both the current to the 2 ohm resistor, and we know the voltage across it. We know the volts were 6 volts, and we know the current coming through this has to be the 3 amps. So there's two things about the 2 ohm resistor we already know. Okay, if we continue to work down, what we know is that across this branch right here, okay, we know that that voltage across that whole branch is what we calculated right up here, our 12 volts. So we can use that information across this branch to help us calculate the current through here and here. Remember that this total current is going to branch out. So we're going to have some current that comes through this 6 ohm resistor, and we're going to have some current that comes through the 12 ohm resistor. So the goal would be now to calculate what are each of those. So we know that across this 6 ohm resistance, right, we have 12 volts. We figured that out before. How about the current? Well, we can now apply Ohm's law, okay, just like we do with regular parallel circuits, Ohm's law to the 6 ohm resistor, and we should be able to calculate the current. So delta V over delta V over R should give us our current, okay? And what we know is that we have 12 volts across the 6 ohms, so we know the current through our 6 ohm resistor should be 2 amps. Now, there's a couple of ways we can figure out the current that must be going through the 12 ohm resistor. Remember that we have 3 amps total coming into the circuit, so if we have 2 amps coming this way, logic's going to tell us, or the sum, conservation of charge, is going to tell us that we have 1 amp, okay, which is going to be flowing this way. Or you could apply Ohm's law again, 12 volts divided by 12 ohms, because there's 12 volts across this resistor as well, would give us 1 amp. So now we know all the information. We know 2 pieces of the information also for the 12 ohm resistor. We know we've got our 12 volts across it, and we know we have 1 amp across it. So the only thing left to calculate for each of these is the power, and remember that power is equal to current times voltage. Okay, so it's pretty simple. We can calculate 3 amps times 6 volts is going to give us 18 watts on the 2 ohm. We've got 12 volts times 2 amps would be 24 watts on the 6 ohm, and 12 volts times 1 amp would be 12 watts across the 12 ohm resistor. If these were light bulbs and we wanted to ask which one is going to be brightest, what we do is we take a look at the wattage. We see that the one with the greatest wattage is this 6 ohm resistor right here. So being that it's dissipating 24 watts of power, this would be the brightest of our light bulbs. That's how you collapse a circuit and re-expand it to do the analysis.